Hello, my dear students. Hope you all are doing great at home. Today we are going to discuss the topic of optical fibers. This is a part of your course Applied Optics at B.Sc 406. Uh, we know that optical fibers are used in transmission of signals, and they are widely used in our networking, computer networking, as well as long distance propagations. We know recently Zio has placed their optical fibers to communicate this long distance transmission of signals from Mumbai to California. So we are getting a very wide bandwidth and effective. That is why we are getting the free internet connections through which we are discussing. We are getting this classes online. So, optical fiber is a technology associated with data transmission using light pulses traveling along with a long fiber, which is usually made of plastic or glass. So, optical fiber is basically made of glass or plastic, and there will be some kind of coating such that this the material which transmit this light will not be scratched, or there will be no damage. So uh, here this various there are various layers in optical fibers, and the construction is shown here in this picture. Here you see there is a part which is called core at the center, then that will be covered by another part which is called cladding. Then there will be a buffer of plastic, and there will be a jacket. So these are uh, the different ingredients, different layers of fiber: glass, cladding, buffer, and jacket. Now let's discuss the construction of it. An optical fiber consists of three basic elements: the core, cladding, and outer coating. The outer coating is comprises of two things. One is this plastic buffer and outer jacket. What core is do? Core does. The core is usually made of glass or plastic, although other materials are sometimes used depending on the transmission of the spectrum in the desire. The core is the light transmitting portion of the fiber. Here only the light, at this core only the light get propagated. Now coming to the cladding. Cladding usually made of same material of the core, but with slightly lower index of refraction. How much? Usually about 1% lower. So this index difference causes the total internal reflection to occur at the index boundary along the length of the fiber, so that light is transmitted down to the fiber and does not escape through the sidewalls. So cladding, the core is having a particular refractive index, and cladding should be having a lower refractive index than the core. Why? We'll be getting it in the principle of this propagation of signals in this optical fiber. Okay, that will be discussed in better way. And what is there? The buffer. The buffer is usually made of hard plastic that protects the cladding from the scratching, which may cause the leakage of the light. Here, this is the buffer, plastic buffer. This buffer is a hard plastic. If this buffer will be not there, there may be some scratching, some bending. Because of bending may appear. If there will be any leakage or scratch will be there in this core cladding portion, then there will be leakage of light, which will be losing our efficiency of the propagated light. To prevent that, we use this buffer. The last one is the jacket, that is usually comprises of one or more coat of plastic material to protect the fiber from the physical environment, and sometimes metallic sheet are also added to the cladding for further physical protection. So that is the final uh, layer of optical fiber jacket. You you can you can see in our physical laboratory uh, the how, if there will be any possibility, I'll be showing you by cutting the fiber what are the layers they are inside the optical fiber. Okay, now coming to the principle. The optical material are characterized by their refractive indices referred as N. The material's index is of refraction is the ratio of speed of light in a vacuum to the speed of light in the material. So that already have been discussed many times. What is called the index of refraction? Say for example, we have a glass material of this. Okay, this let us consider that this glass material is having a refractive index of 1.5. What that means? That means that refractive index is a ratio of speed of light in vacuum and to the speed of light in the material. The material is the glass. Okay. Now, if the refractive index of this glass is 1.5, that means what? We know speed of light in vacuum is 3 into 10 to the power 8 meter per second. If that speed, that is 3 into 10 to the power 8 meter per second, is reduced by 1.5 times. Okay, so that if it is reduced by 1.5 times, then it will be 2 into 10 to the right meter per second. So in this glass, when light will be propagating, then that light will be having a reduction of its speed at 2 up to 2 into 10 to the right meter per second, means 1 by 5 times its speed got reduced. So that will be defined by its quantity, which is uh, how much how much time it get reduced by 1.5 times. So 1.5 will be calling as refractive index. So refractive index gives the information about how, what will be the speed of light inside this particular material. That is the basic concept of refractive index. Now, when a beam of light passes from a material to one material to another with different refractive index, the beam is bent at the interface. That is, we know from the refraction. When incident light comes from a rare medium to a denser medium, then what will happen? The refracted ray will be the light will be bent towards the normal. This is the normal. So this light will be bent towards the normal, and if we think in the reverse way, when a light from a denser medium goes to the rarer medium, then it will be the light will be going away from this normal. So this is the angle of incident I, and this is the angle of refraction R, and what, how much deviated, the deviation angle is delta. Okay, so let's see what the total internal reflection tells. Now coming to this law, the refraction of the refraction is described by Snell's law, which is given by Ni sin I equal to Nr sin R. What is Ni? Ni is the refractive index of this the incident medium, the medium of uh, from where it got incident, and the refracted, this is refracted medium, and that is nr. Nr is the in index of refraction of this medium. And if we have, this is I, means an incident angle, this is R, refraction angle, then according to Snell's law we have Ni sin I equal to Nr sin R. Okay, now if the angle of incident is greater than the critical angle for incidence, typically about 82 degree for typical fiber, the light is reflected back into the incident medium without any loss of uh, a loss by process known as total internal reflection. Okay, that is the total internal reflection. Now if you consider that, if you see from here, this light, if light goes from denser medium to rarer medium, then the light will be bending. If I go on increasing this incident angle, if I launch the light from at this angle, then at some certain point this ray of light, this refracted ray will be at the surface. Okay, that will be calling as the critical angle. If that angle, incident angle, is beyond my critical angle, then it will be coming towards the same medium. That is called total internal reflection. Okay, so here you can see this is, say for example, we have a optical fiber whose this part will this part is a core, this part is a cladding. So core is having high refractive index, higher refractive index than the cladding. So this is denser medium, this is rarer medium. When a light passes goes from denser to rarer medium, if the angle of incident become larger than this angle of critical angle, then it will be reflected back into the same medium. So that will be calling as total internal reflection, and this is the process, this is the principle through which the light propagates through an optical fiber. So in this optical fiber, uh, one parameter is very important, which is called numerical aperture. So what is the definition of numerical aperture? Uh, the numerical aperture is the measure of ability of an optical fiber to collect or confine the incident light rays inside it. It shows the efficiency with which the light is collected inside the fiber in order to get propagated, and thus is one of the most basic properties of optical fiber. So uh, uh, numerical aperture gives the how much light will be entering into the fiber. So that will be giving us the ability of the light that enters into the optical fiber. So that numerical aperture is also uh, connected to an angle called acceptance angle. Now what is the acceptance angle? As acceptance angle is the maximum angle at which light enters the fiber. So here you can see, say for example, this is the light ray which is entering into the fiber. This is a part of a fiber, and let us consider this is the surface at which the light enters. Okay, now the accepted here it is said that acceptance angle and numerical aperture are related to each other. The numerical aperture can be expressed as a sine of the angle of acceptance, or sine of acceptance angle is called numerical aperture. So now coming to the derivation of this numerical aperture, here you can see, uh, let us consider an optical fiber with refractive index. This is an optical fiber which whose core refractive index is n1, cladding refractive index is n2, and the material, the medium one, which is uh, air, whose refractive index is n0. Uh, dear students, we'll be stopping at here. This part will be stopped at here because we have only 15 minutes. We can make 15 minutes video. So uh, next video will be continued from here, from the derivation of numerical aperture. So we are stopping at here. We'll meet in the next video. See my next video also.